Okay, welcome back. And our kind of last formula is the gradient formula. So in part 1 and we're in the third video here. So here we go. This question is, remember that whole rise of a run thing. So we've got two axes here, and we're going to look at an example on the left and then see how we can generalize on the right again. So let's take a point here, and this one I'm going to choose is, what did we, 3, 2. Let's make it the same as before, 3, 2. Hopefully my scale is vaguely right here. And we're going to look at another point over here, which is at 5, 6. So it should be a little bit left, right of that. Okay, so 5, 6. And we're looking to see what the gradient is. So the gradient formula. So if we draw a line segment over here, what's the gradient? What's the steepness? Now, I'm going to put rise of a run like that because we tend to move towards, oh, gradients rise of a run, and perhaps not. But, we need to maybe re-question, why is that the case? So our gradient is, another way is maybe for every one step across, how far up are you going? So let's draw our beloved triangle. We seem to draw this for all of these, so why not do it here? So over here we've got a run here of 2, and we're rising by 4. So if we went, oh, well, our gradient is rise of a run, then we go, oh, well, our gradient is just 4 over 2, which is 2. I'm going to ask ourselves, what does that mean? What does that 2 mean? Now, the 2, one way to think about it is to go, for every one step across, how far up are you going? So if you're going across by 1, how far up are you going? And our gradient of 2 tells us that when we go across by 1, we're going up by 2. So if we're going across by 2, we must have gone up by 4. If we go across by 3, then we must have gone up by 6. So that's that whole rise of a run. We're making sure that for every one step across, how far up are we going? Well, that's maybe one way to think of it. So if we looked at this in general and just see, there's some sort of line segment joining A and B, and we wanted to find out what's the gradient of AB. Again, just getting used to writing these in different ways, the gradient and then subscript little next to it, AB. Or we might go rise of a run. Now let's just think, how did we get that 2 over here for our run? Well, we went from 3 to 5. In other words, 5 minus 3 gave us the 2. So we took the x values and said xb minus xa. And for the rise, we did a similar thing. So we went, well, from 2 up to 6 is 4 because 6 minus 2. So yb minus ya. Now, it doesn't matter if you went ya minus yb, as long as in the denominator you had xa minus xb. And I'll leave it to you to see how they kind of work out the same, regardless of which way you did it, as long as you're consistent. Okay, let's head into 2 examples to see how we might use that. So determine the gradient of the line segment joining A and B. Well, I'm really in the habit of writing gradient is rise of a run. Even though we know it, I don't know why, I just like writing it. Maybe it's a sense of comfort. And so to find the rise and the run, I always start with the run, then I'm consistently starting with my x values, x then y, up to how you do it. Now, before just applying this formulae, let's see how we could do it without applying the formula and going, well, I'm going to run from minus 2 to 3. So how far am I running to get from minus 2 to 3? Well, I must be running by 5. So I can just put a 5 straight up over here. If you prefer to use your formula, so you might have gone, well, I like to use this whole y2 minus y1 idea. Well, you could have gone 3 minus 2. Notice that we're still getting our 5. Depends which one you feel safe or more comfortable with. Try get into the habit of trying both. Okay, let's look at our, well, let's skip in blue, why not? And let's go from minus 1 to 5. I'm still going from A to B. Still A to B, and going from negative 1 to 5. Well, we're rising, I can see, by 6. But if you wanted to do it using the formula, you might go, well, the one y value minus the other y value. Now notice that it looks like I've got that is b, and this part over here is going to be a. So I've been consistent in going b minus a. You could have gone a minus b, and that still would have worked. And if we put that into the calculator or worked it out, notice that we still get 6/5. I'll leave it to you if you would like to do it the other way around and see you should still get 6/5, because of course it would have been -6/5, which would have simplified to 6/5. Okay, one more example. Let's have a look here. So the gradient of the line segment between A and B is -1. Determine the value of t. So in this case, maybe it's useful that we do use our formula and say, well, we know that gradient is rise over run. And again, maybe it just gives us something to work with now. So our gradient is -1. Now, I always like to start with my x values, as I said. I also think it will be easier if we go t minus 4 rather than 4 minus t. Just feels easier to work with, but of course it doesn't matter. If that's the case, then on the numerator, we must go 5 minus minus 2. So we are consistent. 5 minus minus 2. Okay, so if that's our little equation, we can go -1 equals, and as I said, pause, solve as you need to. I'm going to work it out here and go, well, maybe I'm going to multiply both sides by t minus 4. So I'm multiplying -1 t minus 4 equals 7. You may have found the reciprocal of both sides. You may have multiplied that -1 in straight away. There are lots of algebraic ways to think through it now, but I'm just going to bomb through it this way here and say, well, eventually I'm going to get in my slowpoke way here. Well, let's do one more step. Equals -4 from both sides. T equals -3. Okay, does that seem to work? Well, let's look at it just as a final way and say, well, what happens if we were to do this a little bit more conceptually and say, like I said before, gradient is for every one step across, how far up are you going? And this may or may not work, so let's have a look here. So if we're going from 4 to t, well, why don't we go from t to 4? So from t to 4 is our run, and our rise then is going from 5 to -2. Now, we're rising by -7. Okay, so our rise here, so we know, bear with me, that our gradient is rise over run. So we are rising by -7. So we've got a -7 over there. And we know that our run must be what? So that our overall gradient is -1. So here's kind of a downside. You can hear I'm humming and ahhing going, sure, I really have to engage my brain a bit more here rather than just bombing through the formula. Well, this run must be 7, which means we can work out what our t value. So I'm picking up that this isn't quite working, is it? Let's have a look. -1, 5 minus -2, t minus 4. So there's our 7 up top there, and our t minus 4. So where have I gone wrong here? -1, t minus 4 equals 7, minus t plus 4. I need to -4 from each side. Why does that seem? Something doesn't seem right, but this is the point. Also, let's just have a look. T minus 4, this must surely have been a -7 at the bottom. So -3, -4. No, that does seem to work. Okay, so excuse the bumbling. I'm kind of just checking that that works using this thinking. So on the right here, we've got, well, this must be 7. So we must be running 7. So what must t be so that we are running 7? So if we're looking at this part over here, from t to get to 4 must be 7, which means t must be -3, because from -3 to 4 is 7. Now, if it jumps out at you doing this kind of this more conceptual way, go for it. Definitely seems a bit safer to have done this way, even I got myself in a bit of a muddle there, but that's fine. Okay, so that's it for gradient formula. And the last and final video in this part, we'll just look at 2 examples with some concepts of parallel, horizontal, vertical lines, those types of things. So I'll see you then.